theory group there. And it's going to tell us today about the origin. Can I call it the origin of neutrino mixing?
Yeah. So I'm going to talk about neutrino mixing. So let me first start out by outlining what we know about this subject. So we have three types of neutrinos: electron type, muon type, and tau type. And one of the major discoveries in the last 15 years has been that they mix. They change from one kind to the other. This began in the late 1960s when people were measuring solar neutrinos. And they found that the number of solar neutrinos they observed was approximately one-third what they expected. So this is now understood for solar neutrinos to be caused dominantly by matter effects in the sun. Then in 1988, Super Kamiya Kande saw the same thing with atmospheric neutrinos. The expected rate of atmospheric neutrinos was smaller than we expected. So this can be described most economically by having mass eigenstates which are different from the flavor eigenstates. So we have a flavor vector, which is mu e, mu tau, and this is related to the mass matrix by rotation matrix U. Where this rotation matrix called the BMNS matrix contains three mixing angles in one phase. I can write this in the following way. Where in all cases C and S are cosine sign of the relevant angle. This, the first matrix parameterizes the atmospheric mixing. The last matrix parameterizes the solar mixing. The middle matrix we don't know anything about yet. We have no direct measurement on the angles theta 1, 3. We only have a profound on. So this causes a mixing, which I can write in the following way. If I write the probability for a new E to appear as a new mu, so I'm going to write a simplified two-flavor model rather than three, which is sine squared 2 theta, sine squared over E. In terms of a state which is a linear combination. Okay, so this is just basically a generic description of mixing. The time evolution of this state is just given by the Hamiltonian. It's cos theta. And, T. So I have two, in a two-flavor model, I have two states, mu1 and mu2, that are mass eigenstates, and I have cos theta parameterizing the mixing angle to the flavor eigenstates, which is produced. So the question is, can this happen in the standard model? So the standard model has massless neutrinos. So to leading order, the answer to this question is trivial. No mass, then there's no mixing, right? But this neglects one thing. There's no mixing in the standard model in vacuum. But we don't actually live in a vacuum. We live in a theory, or in a universe rather, with neutrinos. So there are neutrinos that are left over from the Big Bang. These have parameters relative neutrinos have a temperature and density that I can relate to the photon temperature and density, which we've measured very well. This is temperature is related by a ratio of the number of degrees of freedom to the photon temperature. And this comes out to be about 1.95 Kelvin. They have a number density, which we expect from standard calculations to be the same between neutrinos and antineutrinos, which is again related by a ratio of number of degrees of freedom to the number of photons. And this is about 56 per cubic centimeter per flavor, per particle into particle. In addition, this system is different than most condensed matter systems we think about, because it has both particles and antiparticles. So I can parameterize this by an asymmetry parameter eta, which is the number of neutrinos minus the number of antineutrinos over the photons. And this is very small. This is related to the baryon photon ratio. This is about 10 to the minus 10. So to a very good approximation, I can neglect the fact that there could be an asymmetry. And I can assume I have a symmetric bath with the same number of particles as antiparticles everywhere.
What about relative dark matter technology?
I'm describing neutrino mixing. Dark matter, I mean, I can give you the parameters for dark matter if you want, but it doesn't affect this. The effects I'm going to show are essentially polyblocking, and so there's not any polyblocking between dark matter. Furthermore, I know neutrinos exist, right? And I'm much more confident of the existence of the relative neutrino background than I am of dark matter. So let's see what it does. So if I take a look at these parameters, and I can write, the relevant parameter I would write in condensed matter, the Fermi momentum, which is the number density to the 1/3. This is about 2.3 10 minus 4 electron volts. This quantity will come up repeatedly. This is the standard object to use in condensed matter physics. It parameterizes the Fermi surface in, say, an electron liquid or something like that. If you've never seen it before, just remember it's the cube root of the number density. I can also write down the measured mass parameters we have. We've got two. The M12 mixing is 8.94 times 10 to the 3 eV, and the other one is 3 squared. So you can see that the measured mass parameters are suspiciously close to the density parameter. So you might wonder what's going on here. These things are not a very good approximation to claim that they're free particles, because they're living in a medium. So yeah.
Sorry, question. The applicability of this Fermi momentum depends on the assumption that everything is in as close to the ground state as possible.
Yes.
Right. Is that why?
Yes.
Is that true cosmologically?
Not necessarily. However, I can consider writing down. So to leading order, what I'm going to do is I'm going to put the density in the problem. And to next to leading order, I consider putting the temperature in the problem. However, the temperature is going to pull in a factor of G Fermi for anything interesting. The density will parameterize polyblocking, and the temperature will be the next correction after that, including electroweak interactions. So for this talk, I'm going to exclusively discuss just putting in the density. So there will be corrections to that, but they will be of order, say, m mu cubed times G Fermi. For instance, a change in the mass due to the interactions, or the temperature would come in something like this. So this could be the temperature as well. So this is really a tiny number. So I want to drop all physics proportional G Fermi for this talk.
And how did the neutrinos get down to fill up the Fermi surface?
It's not that they filled the Fermi surface, it's that I'm not sensitive to any physics other than the Fermi surface, because it's suppressed by G Fermi.
They start out in some Boltzmann distributions.
Yeah, so you start out in in a Fermi direct distribution in the early universe, and this time evolves and freezes out in the usual way. That's where these numbers come from, the temperature and the humidity. So, for the purpose of this talk, this number is simply telling us the density. That's all. I'm not going to describe oscillations around the Fermi surface or anything like
So
that.
you're not going to tell us that there is some sort of false constants or
No.
neutrinos or anything like that?
No. We can discuss that later if you like, but not for this talk.
See, why would the flavors be at the same temperature? You're assuming that they mix, but the equilibrium flavor would have to do with mixing.
Yeah, so they wouldn't necessarily be at the same temperature. If charged leptons were absent, they would all freeze out at the same time, because it's only the weak interactions that are keeping them in thermal equilibrium.
It's a big bang similar to supernova. You expect most of the neutrinos come from Z. Okay.
Yes. Well, not necessarily. It's hard to make that statement. We can the W interactions are stronger, and there are charged leptons flying around. But to a good approximation, you can just assume thermal equilibrium, and this gives you some densities. At the end of the day, so this calculation to get these numbers relies upon a lot of assumptions about the Boltzmann equation, cosmological history, and things like that. I'm rather uncomfortable with all of those assumptions, but this is the prediction that comes out of the standard cosmological model for these things. So I'll put these up here just to give you some point of reference.
All you're trying to say by this is that the neutrinos are lukewarm. Right? The kinetic energy is comparable to the rest now.
Yes?
That's it. I mean,
Yes.
without any prejudice about how they're distributed, this, that, something.
And furthermore, if I want to know the physics of this, which again, so I'm not going to talk about the dynamics of the Fermi surface itself, but if I wanted to know the physics of that, I really don't care about the thermal distribution. All I care about is the pole that occurs because of the presence of the Fermi surface. But again, that's a different talk. So all I really want to do is I want to put the density into the theory. Right? So we have a theory, the standard model, which has no mixing in it, and it has this number density. So how do I put this in? So for this, I'm going to use a tool called mean field theory. Also called sometimes self-consistent field theory. So the assumptions here is I'm going to put in the background field which I'll describe by its state psi. Okay? This I can represent as, I should have done this first, I should do that. Yeah, I'll do this first. So hold on to that thought for a minute, and I'll do this first. Okay, so I'm going to put a state into the theory. This is going to describe the background. And I want to know what operators are going to get expectation values due to the presence of this background. So consider the following operator. This is the spin density matrix. So these are the creation and annihilation operators, the two helicities of a biofermion. Have the positive helicity is the antineutrino, and the negative helicity is the neutrino. So these guys, I put the annihilation operator on the right. So if I take the expectation value of this operator in vacuum, this is just 0, right? But it will be non-zero if I have some particle contact. So I can break up this operator in a couple of different ways. So at the end of the day, what I'm going to want to do is take expectations values of this thing and then fix them. So I can write this in an interesting way. So given a density matrix operator like this, I can expand it in terms of the expectation values of other operators. So consider the following. I'm just expanding this density matrix on a convenient basis, the basis of spin. So this is going to be this should look a little bit familiar. This last one is more commonly called a number operator. This is the number of particles minus the number of antiparticles. Right? So if I found that this had an expectation value, I would call this a chemical potential. But the question is, what are these two? So I can rewrite these in a different way. This is, if I use the field operator chi, so these, some of you may recognize are Majorana masses. These are what one normally puts in for, one of the two choices for putting in a mass for the for neutrinos. So what this is telling me is that when this operator gets an expectation value, it generates a Majorana mass. Or going the other way, a Majorana mass is not a fundamental quantity. It is a quantity that comes from a density matrix. So, okay, so I want to know what this operator is going to be. So let me construct a state and look at its expectation value. Any questions about that, by the way?
Yeah, wouldn't the Majorana mass be the Lorentz invariant?
It is Lorentz invariant.
No, it has a sigma 2. 2 is the vector
It's-
index.
It's surprising, but it is Lorentz invariant. It's not so obvious, but both of these are Majorana masses. They're related to each other by a phase transformation. So I'll step ahead a few steps. What I want to do is that these three are going to be expectation values, and I want to fix them. So I can write for them Lagrange multipliers, which will fix. So I will fix this expectation value with this Lagrange multiplier. The quantity that ends up being physical is mu1 squared plus mu2 squared. And this is the Majorana mass.
This is just for a single flavor.
Yes, for a single flavor. And a little bit of it to bring in multiple flavors. So let's write down a state and let's see what's going on here. So let me consider a single particle. Let me write. Okay, so this is just an arbitrary linear combination of a neutrino and an antineutrino. So I've set it up so that it's automatically normalized. R is between 0 and 1. And this has the following corresponding density matrix. So I can take a couple limits of this. So consider the cases that R is 0. So this would be a pure neutrino in that case. This would give me a row that looks like, okay. I can consider R equals 1. This is variance neutrino. I can consider R equals 1 over square root of 2, and this will give me a linear combination. So I'm going to take just for this example, I'll take that as 0. So this case is actually a superposition. This is a case where I have my state psi is 1 over square root of 2, times my positive felicity plus my negative felicity. So this is the state where I have something going on the off diagonals. And this is the state that is going to give me something interesting going on here and something interesting going on for my own mass. So if I am a neutrino and I live in a background of another neutrino, and that neutrino is a superposition, I will see a Majorana mass in that medium.
Wait. If I'm a neutrino and there's this background, I have to have some interaction to see it.
No, so the assumption is that I'm going to write down a background state, the background field psi, and I'm going to compute with this the expectation value of rho from this side where this is So the essential approximation made by mean field theory is that the anti-symmetrization is neglected between the probe neutrino and the background. So you write down a single self-consistent background state psi and then you expand that. There's no interactions here. Essentially what's going on is only polyblocking. So some of the modes are occupied and I can't create particles in those states. And this looks like a mass. Effectively, this looks like a mass. So I can write here. So for these states, I can write these operators. So in this case, the trace of rho 1, sigma 1, the same as trace of rho 1, sigma 2, 0, and the trace of rho 1, sigma 3 is minus 1. For a pure antineutrino, I have, again, with the trace of the Majorana mass terms, and the chemical potential term changes sign. This is the usual thing that happens when I have I'll go from particle to antiparticles. The chemical potential for a particle bath has the opposite sign to the chemical potential for an antiparticle bath. This one, the superposition, has there's no chemical potential here. But there's still particles in the bath. Something must get an expectation value because there are particles in the bath. And what gets an expectation value instead is this Majorana mass term. Okay. So I can make a couple statements here. This theory has a particle number symmetry. There's a lepton number symmetry which takes the field pi goes to e to the I theta pi. So I can rotate each field by a phase phi, and the theory is invariant to this. A common statement when you have a Majorana mass is that lepton number is broken. But what happens here is that this phase rotation changes this Majorana mass term into this Majorana mass term, and vice versa. Only one combination, namely the sum square of them, is physical, and this is how the mass appears in the dispersion relation. So the theory fundamentally has lepton number. No questions at all?
Is that a problem?
No.
Or I guess it's not a problem?
No.
As opposed to being zero, you're saying? Is that, maybe
So-
I'm not understanding your point. But
So what happens here is that this Majorana mass term I can write as, so a mass term like this, is actually taking particles out of the bath or putting particles into the bath. So I can write this, I can write four possible terms. So I have an imaginary interaction here in which I'm going to take particles in or put particles out of, put particles into or take particles out of the bath. I can write this four ways. I can have a neutrino coming here, a neutrino coming here. I can draw something like this. I can draw something like this. I can draw Actually, let me make this another point. Let me have a pretend interaction. Let's pretend it's a scalar interaction, just to say it right now. And the direction of these lines is really representing time. Okay, so in this picture, I have a neutrino coming in here. This one has to be then an antineutrino, and this one has to be an antineutrino also. So this is a chemical potential. I'm taking two antineutrinos here. This term, I write this way. This is also a neutrino, and then this one is a neutrino also. This term, I have a neutrino here. This is a neutrino here, a neutrino here. This one is a neutrino here. So a chemical potential is an expectation value for one of these operators. The Majorana mass is an expectation value for one of these. You have you simultaneously get a neutrino and an antineutrino out of the bath, or put a neutrino and an antineutrino into the bath. So the lepton number is not fundamentally violated by the global theory here. However, if I do an experiment in which I only have one neutrino and I expect it to show up after it's propagated some distance, these processes are going on and it can exchange with the background.
In your third case, you are still in a pure state. I assume the neutrinos in the whole universe are in a coherent pure state.
So yes and no. So in order to do mean field theory, I have to make a couple of assumptions. One is that I have a single state psi. Okay, so I could consider writing down a mixed state, many states here. So in this case, I have psi for a fermion system is what's called a Slater determinant. This is object looks like this. The point of writing this down is that fermions have to be antisymmetrized. So if I exchange the coordinate locations x between two states, the state has to flip sign because they're antisymmetric. So mean field theory makes the assumption that your background is a single state. It's a single Slater determinant. That forces you to be able to write the system in the following way. So I can write an operator V, which is okay, and I can write my density matrix rho hat in terms of V, which is just right here. Okay. So this means that my expectation values are often the same way. So the expectation value of this guy will also be able to be written this way.
But then aren't you actually telling us that in a certain sense neutrinos behave like a quantum?
Yes.
But I thought that initially you said you didn't want to make that assumption.
So what do you mean when you say condensate exactly?
Well, I mean that they're coherent.
What do you mean when you say coherent exactly?
But they're not in a density matrix.
There is a density matrix which
pure
can
state, not a
Yeah,
mixing.
exactly.
So this assumption here means that the density matrix rho equal to rho. This is to say the density matrix is idempotent. This is also usually called a pure state. This is a consequence of the assumption that you have a single state representing the background. This means that there is no time evolution in these coordinates.
Why would the universe, we understand that, but why would the universe that started with completely coherent such a random state evolve to this? In the absolute terms?
So the basis in which I'm writing rho is that of spin. So that what this statement says is that the spin configuration is stable with respect to time evolution. There is no rotation between neutrinos and antineutrinos. There is an expectation value for the number density of neutrinos and for antineutrinos, but that is a pure state. Now the thermal distribution is absolutely not, right? That's a Fermi Dirac distribution that's been redshifted, and this condition would not hold if I were to write this in terms of the temperature, in terms of momentum modes.
So is this supposed to apply to our universe or not?
Absolutely.
And how did the spins get into this pure state?
How do the spins get into this pure state?
All the
I need
neutrinos
a
were in some
state,
thermal
right?
state initially.
No, but the whole
All the
point was
spins
they
were
were
random.
all random initially. They acquired the spin virtual particles colliding with stuff at very high energies, theoretically
If
and
it-
stuff.
It's in pure state has zero entropy.
Yeah,
How do you
exactly.
No, this does not have zero entropy.
A pure state has zero entropy.
By definition.
This state does not have zero entropy. I can write down, I mean, there's a number density n log n is not zero. If I write down a thermal distribution, if I write the density matrix in momentum space, rho log rho is not zero either. Yes, so the system absolutely has entropy. That's part of the point. Is that so I'll get to this in a minute, but one might conclude, if one does not put this operator in, that there's no entropy in the system. There's no number density if I don't put this operator in. If there's no number density, then there's no number, and then n log n is zero. So the description of the system with a chemical potential but no Majorana mass is the state with zero entropy. That is the state in which I have separated the neutrinos from the antineutrinos.
I'm sorry, I'm still trying to understand what you mean when you said that that you're talking about the spin state here. I mean, a Slater determinant anti-symmetrizes the total state, including position and spin, or momentum and spin. So why is this not your psi here then is the total state of the
Total state
system
all
of
of the
neutrinos.
background neutrinos. Yes.
Okay, and that is a pure state, you say.
In the spin basis, yes.
I don't think that purity is basis dependent,
So-
is it?
Well, no.
Well,
Look,
you-
if I were to write this in
you
momentum
say
space,
the same-
they are not in a coherent temperature. They don't all have the same energy. Right?
Yeah.
So it's not coherent in that sense. It's not a pure state in momentum space.
I'm sorry, I don't understand what that means. I mean, you can choose whatever basis you want. Are you saying in momentum space if you trace out the spin, or
Well, in this case, I'm tracing out momentum.
you are? Where?
Yes.
Where? Okay,
So,
that's
sorry.
what I'm missing.
So I should, yes, I'm sorry, I've suppressed momentum index in all of these operators. And then taking the expectation value, I'm integrating over momentum. Sorry, that was,
Okay,
all
that's
of
so,
these should have be functional momentum. This is a spin density matrix for a single momentum node.
okay, so the density matrix for which rho squared equals rho, is that before or after you've integrated out the
After.
momentum?
After.
After,
Yes.
okay. Then why do you expect, why is it, why do you expect anti-symmetrization then if you've integrated out the momenta? I mean, it's not true.
This state is not yet integrated out the momentum.
Oh, okay,
I'm just describing the general system.
okay.
Is a Slater determinant,
Mhm.
where each of these sides is a 2x1 matrix in spin space.
Okay.
So the one you were saying something?
No, no, go ahead.
Okay. So, okay, so this is
all,
the description
so all
of
the
the background.
neutrinos in the universe have their spins in some pure spin correlation.
In the sense that this nomenclature is confusing. The strict statement is that if I want to use mean field theory, I want to choose a single background state. That single background state is a Slater determinant. That choice gives me that rho squared is equal to rho in the spin basis after I take the condition.
But since we don't expect the spins to be in this coherent state all over the universe,
Well,
it tells us mean field theory doesn't apply to a state where
So what does that statement mean exactly? What kind of spin configuration are you expecting?
expecting a random, completely random.
Mixed
So this is-
example.
This is random. Psi 1, Psi 2, etc. I can choose to be anything I want.
You're saying after you integrate over momentum or space, you get this pure
Yes.
density increase. But it's not random.
But it's only in 2 by 2 matrix. I mean, there's only 2 parameters in that matrix. There's a phase and there's a magnitude.
But you're assuming that it has a particular.
Yeah, if it has this particular, if I measure the neutrino here with spin up, then the neutrino in the whole universe will collapse into that spin up state.
So part of the
That's why
assumption
they
here,
are-
part of the assumption of
Without-
mean field theory is that I'm dealing with plane waves. So there's no sense of localization here. The state, I probably should write momentum here rather than position, but this is a state of plane waves.
And so if we know the spin of one cosmic neutrino, we know the spin of all the neutrinos in the universe.
No, not at all.
Okay, so the idea here is that just that since everything is totally anti-symmetrized, once you integrate out the momentum, that gives you a correlation among the remaining spins, right?
Essentially, yeah.
Um,
This is to say,
So-
in some sense, I know how many neutrinos there are, I know how many antineutrinos there are. I know what the expectation values are for the number of neutrinos and expectation for the number of antineutrinos. I'm not making any statement at all about the momentum distribution. So, I believe this is equivalent to saying the number of neutrinos is equal to the number of antineutrinos.
And that's just to say that two diagonal entries are equal. In general, mixing samples is off diagonal.
Yeah, so this matrix has off diagonal entries. So, in this case, so this condition rho squared is equal to rho forces me to have this phase phi equal to theta. There's only one phase for a single state with a single momentum. Okay. Okay, so yeah. Right, rho squared equal rho implies that so I wrote it here, 2 phases, theta and phi. The condition that for a single neutrino that this thing, the idempotent, so rho 1 squared equal to rho 1 implies that these 2 phases must cancel. So theta is equal to
So
phi.
are you saying you're making an even stronger assumption than just being in a single?
No, I'm saying the assumption that I have is I can describe the background by a single state implies rho squared equals rho. Implies that these 2 phases have to be equal.
Second, if you start by assuming that you're in just a single background, I can pick a single background that has theta and phi different, right?
Why?
Because that's just a single state. Your assumption is, your ingoing assumption is the background is described by a single state. So
Yes.
that you pick a single state where theta and phi are different.
Okay.
And you're saying that alone is enough to get me to rho squared equals rho.
Yes.
So then, how do I get this additional assumption that theta and phi are equal? Well, what extra condition goes in to tell me that theta and phi have to be equal? What buys that for me?
And why don't you just absorb theta and phi into a dagger from the very beginning, and we don't even have to write them down.
square that matrix, it's not equal to itself.
No, unless,
But that's the general form.
that is the general form, yes.
So there's some additional assumptions.
I think the statement would be, and this is a single quantum state, right? It has to have a single phase. So if I put two phases in my quantum state, that's kind of a strange thing to do. This, therefore, must be a mixed state. I have to write psi 1 plus psi 2, well, there are two different states with two different phases in order to get theta and phi not being equal to each other.
That's not a mixed state, that's just a superposition of states.
Yes, but in terms of this background state, it is a mixed state of two background states. Okay, so we can discuss further what exactly means to be a pure state. Not just be interested, but so let me continue here.
I had another question.
Yeah.
In your diagram, what's that dashed line?
Some fictitious interaction. So if I propagate from A to B, let's say it's the propagator,
Propagator of what?
the neutrino.
No,
I'm just trying to
neutrino lines
depict
are already-
how, I'm not trying to find a diagram. I'm trying to depict how I can absorb neutrinos out of the background and put neutrinos into the background.
You
There's
have to
no-
have some scalar that propagates from
Yes.
two vertices.
Or I can just have a 4-point interaction. Yeah, so I mean, if you want to consider this a weak interaction or something like this, you can do that. But I don't need a weak interaction to do this. The propagator alone is enough to exchange with the background in the absence of any interaction, because it's simply polygon. I can,
Well, if there's no interaction, then it's just two disconnected diagrams.
I didn't want to get into this, but you can write an interaction. So I'm going to, for the purpose of this talk, constrain the moments of rho expressed in the basis of column matrices. So there's another operator I can write, and that's rho squared, which I can write as a single operator. So there's only one 4 Fermi operator for a single fermion, and it's this one. This is the same whether you're considering Z-boson interaction or the moments of the density matrix. This is an effective interaction caused by polyblocking. So if you want to use that interaction here, you can.
Well, maybe, if we ignore say there's no interaction,
Just rows.
the neutrino coming in on the left has some momentum, the one coming out on the right has completely different momentum. Because it's just coming out of the background, which has some momentum distribution.
Yes. So in that case, when we want to write,
So we
in
would
terms
see
of
that
Feynman diagrams, we want to write this.
neutrinos, momentum of neutrinos is not conserved because they go in, absorb into the vacuum of one momentum and pop out with a different momentum.
So, yeah. So in terms of Feynman diagrams, I can write it this way. I have this effective 4 Fermi interaction here caused by polyblocking. I have a loop. So the loop can have a different momentum now when I'm propagating neutrino. And that's why I can see the lower momentum in neutrinos in the background.
But now it's not a propagating neutrino because it doesn't conserve momentum.
It does conserve momentum.
The
This
bottom
diagram
diagram,
conserves momentum.
the one below with no dashed line,
Okay, so if you want to consider particles, this is for particles that are already in the bath. If you consider a particle that's not in the bath, I should draw this diagram. Because as you say, otherwise I will not know about the background because I'm high energy.
well, in the bottom diagram, I can insert an extra neutrino, it's absorbed by the background, and then some other neutrino from the background pops out with a different momentum. Because you have this background,
Yes. Okay.
neutrinos with arbitrary momentum.
Yes. So if I was able to do an experiment and create neutrinos that had energies of order of temperature, yeah, at the target, there's no guarantee that the neutrino is easily the one ascent, it would easily be one in the background. And this would not consume momentum.
But I wouldn't call that a mass.
Well, the operator is traces of the density
I
matrix.
want to go back to John's earlier question then. So if momentum is unconserved, it sounds like it's not Lorentz. It's not a Lorentz invariant.
Momentum is conserved. The diagram which conserves momentum is this one.
But it gets its maximum exchanges from the background, right?
Yes.
And the exchanges, this virtual sort of loop diagram with the background is the thing John's talking about, one neutrino disappearing and another one coming out. So a mass insertion in this theory also raises the possibility that you don't conserve momentum. Or is that too quick?
No, I mean, so if I write this diagram here, I have some momentum P and some momentum P. This loop has momentum P plus K. So this loop goes all the way down to because K is a loop momentum, I integrate over it. This high momentum P can see the background with very low temperature. So the exchange occurs in the loop. I'm just trying to kind of picture graphically what exactly what's going on, but strictly it's this. Okay, so the next step I want to do is, now that I have these operators, I want to constrain them. So for this I'm going to use a Lagrange multiplier. So given that these operators have expectation values, I want to now constrain them. So I want to add my Lagrangian. So I have some Lagrangian function of field. I'm going to add to this traces of rho I sigma times some Lagrange multiplier. What this does is it fixes the expectation value of this operator for particles that are propagating in this medium. So I should add, so one of these is a chemical potential, the other two are Majorana masses. So I should add to the standard model 2 Majorana masses, or 1 Majorana mass of this phase argument to describe this background. So our universe, as it sits today, looks like the neutrinos have mass due to these operators. So what does this mass matrix look like? So far I've been considering a single flavor of neutrino. If I consider multiple neutrinos, so let's consider 2. The dimensionful quantity that is the mass is the Fermi momentum, which is again 3 pi squared times the number density. So if I write more than one field here, I'm going to have the following. So my mass matrix for 2 flavors looks like this. So on the off diagonal here, I have operators which contain one flavor of an annihilation operator for one flavor and a creation operator for another flavor. So if you remember back to the harmonic oscillator, if I have the state psi or state n, and I have to put on my annihilation operator, this gives me back n times n minus 1. And a dagger on and gives me
I think we'll forgive you this one, don't worry about it.
so this is the origin of these off-diagonal terms. I'm taking the limit that the number is very large, so that I can drop the 1 here. So I have only these off-diagonal terms. So if I diagonalize this matrix, the angle that diagonalizes this theta is the arctangent of n1 over n2 to 1/3. So this system, if n1 is equal to n2, this has very large mixings. So this is 45 degrees if n1 is n2. Yep.
using the Fermi momentum as if we're filled up to some level.
Yes, because that's all I care about, is counting the number of states in the system.
But
I'm not
really,
sensitive to the
we have
thermal
some
distribution.
Fermi-Dirac distribution. And so the states below Fermi momentum are not completely full. And so I can have states propagating down there below the mass.
Yes,
So it's not, doesn't act like a mass.
not in the low momentum limit, no. I mean, this is the appropriate description in the field theory, and in the approximation, the high energy approximation, it is, it looks like a mass. Obviously, if I were able to make an experiment close to the momentum distribution, and I was able to see exactly which momentum modes were polyblocked, I could map out that thermal distribution. And it would clearly not look like a mass. But then I should not be doing mean field theory in the first place. I'm sensitive to the individual momentum modes of individual neutrinos, and I'm not. This is averaging over all of them at the same time.
If you've got, if you're
Well,
looking
the main question is, I mean, really, I mean, you know, this term that you think that behaves like a mass. In fact, I might buy that. That in fact, if you prepare a background state in which, you know, you do something like a Hartree Fock.
Exactly. This is exactly her.
I understand. I mean, you know, and then you sort of take the expectation value of n-1 particle wave functions in that special state, and then look at the effect of that on the remaining one particle, and you do separation variables, and there is an integration constant that appears to separate variables, which depends on the main question is the coherence length of the n-1 particles, you know, into that thing that has to have that coherent phase in order to behave like a mass. The moment, you know, so that's some fixed length, and yes, it may be true that
So what do you think that this size would be?
I don't know. I mean, but what
I'll
I'm
tell you
trying,
what I think the size would be.
well, what I'm trying to say is that I can't see how that would actually be big enough for the
So,
energetic particles, even
So what
lower
you're saying
energies,
is-
to see that it's.
What you're saying is locally you want to make a perturbation of the spin density distribution. Locally you want to make local overdensity neutrinos or local underdensity neutrinos. This, so this you can evaluate. So imagine I have a single neutrino, right? Imagine I want to make
you
it,
think it's a millimeter,
I think it's a gigaparsec.
a gigaparsec. Wow. No, but then, you know, why would
Because
you-
that is the size of the, I mean,
No, that's horizon, but you're basically
Yes.
saying that neutrino spins are, I mean, this is literal. You really are telling us that you have a condensate across the Hubble spin.
it is not a
Spin
condensate.
condensate. It's a spin
Yes,
coherent.
Yes,
So
so
we
within,
live in a spin crystal.
no, it's not, but it's not like a condensed matter system. I mean, this is not a crystal.
Yes, I know, but if you're telling us that it looks like it because in fact
Yes.
it has the same, I mean, you know, that's very hard to believe.
Why?
Well, you know, because of the fact that there is something called causality and local interactions which operate over
This
much,
is
much
entirely
shorter
local, this is
scale.
entirely causal.
At high energies, these neutrinos are running around Hubble, at Hubble, over Hubble horizons in the old days, so to speak, which are like a light second across. At nucleosynthesis time. They're running around, they're colliding, they're rearranging.
Okay, sure, fine.
You know, and then
that's
suddenly
not the
all
system
of
I'm
these
describing.
little guys that are being processed. No, but your system has to evolve out of all this.
Yes.
So I don't know.
Okay,
how-
so let me give you a different argument. So, if you assume you have localized neutrinos, I'm going to make local density perturbations and make local spin distributions. Now, let's take the most conservative possible case. Let's assume that
If, by the way, if the Fermi level were completely filled up, which it is not, because the neutrinos are still
it
lukewarm.
doesn't have to be. Why would it have to be?
Because otherwise it's not going to stay coherent.
If
over
my
such
energy is much
space.
greater than the temperature, it doesn't. I don't require coherence.
Well, if,
Yeah.
if you're just doing a Fermi level type calculation and you're looking at energies above the Fermi surface, there's no interaction. Why does the Fermi surface have any effect?
Because of polygon, because of this diagram.
But I suppose when I'm thinking of doing some condensed matter problem, say in Griffiths with non-interacting matter and just seeing the quantum pressure build up by putting particles in the box, the behavior of the basically at zero temperature, Pauli blocking just acts like a delta function. I can't access these states as can't scatter into them, but it's that states above it
Yes.
are basically unaffected.
yes,
So
if-
something that's propagating along wouldn't even feel the Fermi surface unless the neutrino.
But if I have a self-interaction, which comes from the polyblocking itself, this is the trace of it's not row square, it's a determinant of row. This operator is an effective four-Fermi interaction. It also has an expectation value, just like the density matrix. So I can write down this four-Fermi interaction. This is also coming from an expectation value of background. This means I can draw a usual
Between having
finding
an
group.
expectation value and having new interaction with the requirement.
If an operator that is a four-Fermi operator has an expectation value due to my choice of state, which it does,
Well, that's the main question, that whether your choice of state describes the universe. That started out random in simple causally isolated patches may have had.
let me answer this question. Okay, so if I have a causally isolated patch, let me assume let's call it a single neutrino, okay? Let me assume its wavelength is a millimeter, okay? I can then compute the uncertainty. So what you're saying is the uncertainty delta x is millimeter, right? So at a single time, I'm going to create a state that's that localized. I can then take this system and then time evolve it, right? The time evolution of this state evolves very, very rapidly because these are relativistic states. Their mass is very, very small. And so this local density perturbation you want to make will evolve with the speed of light. I can ask, I don't have the formulas with me to write all this up, but I can ask, how long will it take before this density perturbation is larger than the interparticle spacing? And that is approximately a picosecond. I can ask, if I started with a density perturbation in the early universe, let's say its localization was an MEV, and I evolved it to now, I let it expand for the age of the universe. The size of that density perturbation now is order 10 gigaparsecs. This is the paper by Fuller and Kishimoto, as well as the one by myself.
I think the argument everyone else is, with Mania is running is in the opposite direction. He's saying you've got a picosecond before your wave function collides with something else, and then it's no longer isolated.
And then
That's no longer
at that
coherent.
point, I can no longer see individual wave functions. I have to consider their sum. And that's exactly what I'm doing. So let me write up the last thing and I'll be done. Okay, so I wrote down the two mixing case. I can write down the three neutrino mixing case. Then I have a mass matrix that looks like this. It's the same as this one for 3. Symmetric. This can be diagonalized by J1 to arctangent of and another angle and the final angle theta 1 3 is 0. If, for instance, I have n1 equals n2 equals n3, which we expect from the cosmological predictions, this is known as tridynamical mixing. And it has, in terms of the sine squared of these angles, is 1/2. This one is 1/3. The other one is 0. I can write this another way. I can write the, taking these formulas, I can compute the neutrino mass. So the electron type neutrino has a mass delta m to 1 squared sine squared theta 1 2. And this comes out to be this theory only has 3 parameters. There's only 3 densities. The mixing angles are not separate parameters. A couple final points. The system has no CP phase. This is partially because theta 1,3 is 0. An intuitive way to think about it is because the system has no parity at all. I have all left-handed fields. There are no right-handed fields present at all. So it can't have any CP violation. There's no parity operator at all. Finally, there's no Majorana phases. So in general, I can write down an additional phase related to the rotation between the 2 types of Majorana mass terms. Because this system has lepton number, I can rotate away that phase, and so it's unphysical. Okay, so I claim, in conclusion, the standard model has neutrino mixing. It comes from the relics. And using this, there are 3 parameters, and we can calculate all of the mixing angles already. I have 4 measurements of the mixing. There's 2 mass differences and 2 angles. So that's it.
Any more questions? Sorry, I didn't want to disturb everyone walking back here.
Well, experimentally, because we know that try by maximal efficiency isn't correct. It's not.
It's close. Well, this is assuming N1 equals N2 equals N3. Better way is to do it the other way around. Measure all the mass differences and the angles and predict the masses. And it works fine. So I can put up some other numbers. So this piece of the talk is new. So I just did this this morning. So don't hold me to these numbers. But using the measured mass differences, I can compute all the rest of these as well. This is in the normal hierarchy. So a very interesting test of this is whether these mass relations hold, especially once we have experiments that can kinematically measure the masses directly. Furthermore, a solid prediction of this is that they are Majorana. So we will see them in the day-to-day experiments.
Why are the mass? So to get oscillations, my mass basis and my weak interaction basis have to be different, right? But so in the absence of weak interactions, it looks like the Pauli exclusion principle only applies to identical particles, so the mass basis should be identical. To each one should act exactly the same way. Because in the absence of masses, in the absence of any interactions, they're all just 3 copies of exactly the same thing, right? The only thing that distinguishes the neutrinos are
But on the off diagonal here, I can write, for instance, A for mu, a dagger for mu e. This has an expectation value in back. This is what's going into these off-diagonal operators.
You're saying the masses are determined by some initial condition of the condensate.
Yes, or rather by its state today. Yeah, I mean we're measuring the state.
But there's nothing in the Lagrangian that tells you what that state would be. It's just,
Lagrangian is the standard model Lagrangian. It has massless neutrinos.
But I suppose the thing that I'm having difficulty seeing is why such terms arise in a non-rotatable way.
They are rotatable away.
If I had no interactions, it seems like it could just rotate it all away. And then if I add interactions in, then why would the
You can write this-
mix up?
So I have to have operators for this. I can relate this to the entropy of mixing. So first of all, there's an entropy here, right? So I can write n log n for a single field, right? For a second field, I can write n1, n2 log n2. But that's not all. If I mix 2 systems, the entropy of the mixed system is actually larger. And that's what, in some sense, that's what these off-diagonal operators are parameterizing. Is the additional contribution due to mixing. Mixing meaning mixing 2 systems, not mass mixing. But
the bronchium has some exact rotation flavor symmetry between all three types of neutrinos. Just condensate apparently does not share that symmetry, so there's
Yes,
spontaneous symmetry breaks.
Because N1 is not equal to N2, not equal to N3.
So there's a Goldstone boson. There's 8 Goldstone bosons or something.
In fact, there are, which is something I would like to discuss while I'm here. These would be density oscillations, density waves.
Any more? Not to think about.